Okay, let me start first pre-class lecture for second day. So for second day, I will review lattice studies of B physics. So in this pre-class lecture, first I provide a brief introduction to new physics search in B physics. Namely, I discuss relevant processes in of new physics obtained so far and problems. And then I will review lattice studies on leptonic decay. So here I list several B-meson processes mediated by double boson, namely with Quark-Leber changes. And the leptonic decay is simple because it doesn't have hadron in the final state. But the decay rate is suppressed by lepton mass squared due to the helicity suppression. And due to the parity symmetry in QCD, only weak axial current contribute to the leptonic decay. On the other hand, semi-leptonic decays has a hadron in the final state, and hence we have additional kinematical variable momentum transfer carried by W boson. And again, due to the parity symmetry in QCD, the only vector current contribute if the final state hadron is the pseudoscalar meson. And neutral B-meson mixing is expected to be a good and sensitive probe of new physics because it is a so-called flavor-changing neutral current process. So its standard model contribution is loop suppressed. And there are other loop suppressed processes called wear decays. And while it is rare, but it is experimentally easier to observe if all final state particles are charged particles. And here I list the past and ongoing experiments. So the KEKB Bell experiment at KEK and the Baba experiment at SLAC have been completed around 2010. And these are the E plus E minus collider and generated about a million PDB pair and carried out various measurements about the B physics and charm physics and tau lepton physics. And this Bell experiment has been upgraded to the Super KEKB Bell experiment at KK, and this has been already in operation from 2019, and it will accumulate 50 times more data compared to the Bell experiment by 2031. And these experiments are good at the event process. So these are good at measuring the processes with neutrino, such as the leptonic decay, semi-leptonic decay, and wear decay with neutrino in the final state. On the other hand, the LHCb at CERN is a proton-proton collider, and this produces many and various B hadrons by high energy collision of protons. So this experiment is good at measuring the real processes without neutrino. And since these experiments are designed to generate produce BB pair, so compared to this, LHCb is good at the physics of other B hadrons, namely that BS meson, BC meson, and B hadron, B baryons. And thanks to previous past experimental and theoretical efforts, there are several hints of new physics called B anomalies. And this left figure shows the lepton flavor universality violation in P2D style new decay. So this figure shows this decay rate ratio between the tau lepton mode and light lepton mode, or the B2D style decay and B2D decay, real new decay. And this ratio is sensitive to the Higgs-like particle, such as the charged Higgs predicted by supersymmetry. And there has been more than 3 sigma tension between the standard model and world average of experimental data. But if you look in more detail, you can see that there is a significant deviation between the new latest new Bell measurement and past old Bauer measurement. And this deviation should be resolved by ongoing measurement by Bell 2 and LCB. And this right figure shows an angular observable for P2K star LL decay. Actually, and this figure shows the so-called P5 prime defined like this. And you don't have to understand this definition, but you can simply consider that this is asymmetry about the decay angles. And there has been more than 3 sigma tension between the experimental data and standard model, and it persists from its first observation in 2013. But you can see that there are harmonium resonances here and here, and at the moment we cannot rule out the possibility that these deviations are due to our poor understanding of the non-perturbative effect from these harmonium resonances. And there are other tantalizing 2 to 4 sigma hints also for the P2K LL decays and BS25 LL decays. But there has been a long-standing problem in the determination of the CK matrix element. So to discuss that, first let me introduce the role of the lattice QCD in the determination of CKM elements. So lattice QCD can study the leptonic decay, semi-leptonic decays mixing in kaon physics, charm physics, and boson physics. So lattice QCD can provide a crucial input of the hadronic matrix element to the determination of many CKM elements. And now these decays and mixings provide a standard deviation of these elements together with lattice QCD. So namely that the kaon decay and D and DS meson decays and B meson decays and B meson mixing. And lattice QCD also provides a non-standard determination by using, for example, BS meson decay. And lattice QCD now also provide information about long-distance electromagnetic collection for the superload nuclear beta decays to determine VUD, and KO and pion leptonic decays to determine VUS. And in order to search new physics, we can check the consistency among these independent determinations. And we can also check the standard model condition, like unitarity, by using, for example, unitarity triangle derived from the orthogonal condition between the first and the third column. But there has been a long-standing problem in the exclusive and inclusive decays. So the exclusive semi-leptonic decays means that semi-leptonic decays with the final state hadron specified. So the whole P2C transition, these include the B2D new decay, B2D style new decay, B2DW style new decay, and so on. And QCD input to these exclusive decays are the matrix element of the weak current between the initial and the final state. On the other hand, inclusive semi-leptonic decays is the decay summed over final state hadrons. So for B2C transition, this is the summation of the over the B2DL new, D style new, DW style new, and all other possible final states. And then inclusive decay rate is given like this, and through optical theorem, it can be written like this for the B2B matrix element of the product of the actual current. And then by OPE, it can be written like as the summation over the B2B matrix element of the local composite operator. So QCD input to the inclusive decays is the so-called heavy Quark parameters, such as the B2B matrix element of the non-relativistic kinetic energy operator and magnetic moment of interaction operator, and so on. And since this analysis involved the OPE, namely the double expansion in terms of the strong coupling and 1 over MP, the convergence of this double expansion is a very important issue. So at the analysis level, inclusive decay is not a simple sum of the exclusive decays. So these analyses have the very different systematics. And there has been long-standing tension between the exclusive and inclusive decays in the VUB and VCB. And in this figure, this band shows the result from exclusive decay. So VUB from B to pi nu and VCB from B to D cell nu and DL nu. And this symbol shows the result from inclusive decay. So there is a significant deviation between the exclusive and inclusive decay. And these are the 50% and 3 sigma tension for VUB, and at most 8% and 4 sigma tension for the VCB. And this discrepancy is very larger than the expected accuracy of current precision measurement. So without resolving this discrepancy, the impact of the ongoing experimental measurement will be largely diminished. And in the literature, there has been a discussions that it is unlikely that the new physics is the source of this deviation. So we have to say that this tension is due to the poor understanding of the theoretical and experimental uncertainties, and we need deeper understanding by theoretical and experimental studies. So in the following and the next class lecture, I will review studies of B physics with particular focus on the determination of CK matrix element. So in addition to the usual reference, namely the particle data book and review by the heavy flavor averaging group, I introduce these two helpful references. So first is the review by a flavorless averaging group, Quark. And in their review, they rate the setup of the existing simulations as the good, so-so, and unsatisfactory, and then they provide a world average of good and so-so results. And they have the long history starting from 2010, and their latest, we expect their latest review in this year. And actually, I'm involved the VUDP section of this blog review. And another reference is the white paper by the Bell-to Theory Interface Platform B2T. So this white paper summarizes the impact of the Bell-to experiment to the new physics research. And again, I involved this working group activity. And in this talk, I will not try to derive my world average, nor provide a very comprehensive review. Instead, for fundamental processes, I will try to introduce the background physics and the future prospect and the current status based on these differences. So in the remaining time, let me review Lattice study of leptonic decay. So the hadronic matrix element is the B2 vacuum matrix element of the weak axial current, and it is parameterized by the so-called decay constant, depending on the Quark masses and lattice spacing. And compared to other processes, the leptonic decay is easy to study on the lattice because the hadronic matrix element can be extracted from the two-point function without momentum. And then results at simulation points can be extrapolated to the continuum limit and the physical Quark mass by using this kind of form, namely the non-analytic term predicted by heavy meson perturbation theory plus polynomial correction in terms of the Quark masses and lattice spacing. But this leptonic decay is experimentally not easy to study due to the heresy suppression. Indeed, the branching ratio is the 0.01% for the B2 tau nu decay and 0.001% for the B2 mu nu decay. And actually, to my knowledge, this B2 mu nu decay haven't yet been observed. And I also note that due to the parity symmetry in QCD, only axial current contribute to the leptonic decay. So So we may say that the leptonic decay provides a selective probe of new physics. Namely, we can selectively study the parity of new physics interaction by using the leptonic decay. And here is a list of the Lattice studies or Lattice calculation of B and BS meson decay constant. So these are the calculation in 4-flavor QCD and 3-flavor QCD and one from 2-flavor QCD. And you can see that there are many calculations of these decay constants. And by checking heavy Quark formulation, all of the relativistic approach, HQT and static limit, and non-relativistic Lattice QCD, and the Fermi-Lab approaches have been used. And so these decay constants have been calculated by several collaborations using different heavy Quark formulations. And we confirmed good consistency among different heavy Quark formulations. And maybe this consistency can be easily seen in these figures of the FB and FBS. And if you look into the details, you can see that the average for 4-flavor QCD is dominated by the very precise numerical result. So we need more population calculations for 4-flavor QCD to firmly establish lattice predictions. And this is a VUB determined from the leptonic decay rate. And you can see that the much larger uncertainty comes from the experiment due to statistics. And it will be improved to 3% level by level 2. So the accuracy will become competitive to that from semi-leptonic decay. So by that, with that precision, this leptonic decays provide a third independent determination of VUB in addition to the conventional exclusive and inclusive semi-leptonic decays. And this determination is really helpful to resolve the VUB tension. And the decay constant of BS meson, namely FPS, there is no leptonic decays corresponding to the FPS. And actually, FBS describes the B2LL, BS2LL rare decay. And this is the standard model diagram for the B2, BS2LL. And its decay rate is written like this using the FBS decay constant. And so this is the loop suppressed diagram. And this is because the fact that there is no FCNC at the tree level in the standard model guaranteed by GIN mechanism. So this loop suppressed process is expected to be sensitive to new physics. And actually, this process has been already measured by CMS and LCD in the 2014, and the BS2 mu mu is significantly measured. But BD2 mu mu hasn't yet been clearly observed. And standard model prediction for the BS2 mu mu is consistent with experimental measurement, but significantly smaller uncertainty. So that we can say that FBS appearing in this decay rate expression has been determined sufficiently precise. So let me summarize this pre-class lecture. So here I provide a brief introduction to B physics and review lattice study on leptonic decays. So B physics provides a main field in intensity frontier, and it covers various processes, and past and ongoing experiments provide accurate experimental data. And there are some anomalies observed in semi-leptonic and rare decays, and long-standing tension in CKM element has to be resolved. And leptonic decay is relatively easy to study on the lattice, but not easy in experiment. And there are many independent calculations with different heavy Quark formulations, and we observe the good consistency. And very good to make the VUB determination from leptonic decays comparative to that from semi-leptonic decay. and the decay constant FBS is relevant to the efficiency process based mu observed by LCD. Okay, that's all.